Hello, everyone. Thank you for attending this dynamic thinking webinar. My name is Dylan Gondyke. I'm an applications engineer here at CNC Software, and I've been in the industry on and off for about 16 years now. So let's dive into the heart of this webinar. So driving complex multi-axis motion using simple geometry. So when you step up from a 3-axis world to a 5-axis world, things really open up. You enable the full 6 degrees of freedom. You are basically limited only by your imagination and by your fixturing in terms of what you can cut and how you can cut it. And to drive the tool motion for this, we need to understand how to program this in a manner that we will be able to picture and edit in the future. So when you look at a multi-axis path or a surface that you're going to be pathing, you have this picture in your mind of what you envision the tool motion to be as it crosses that surface. So how do you translate that from your mind to a finished tool path that you're posting and running on the machine? And there's 2 core concepts that enable that for multi-axis machining. So multi-axis toolpath generation is all about control. So cut pattern control and tooltip control are concepts that are familiar to you from 3-axis programming. And to go from 3-axis to 5-axis programming, we have to take into account 2 different methods of control. And we are adding in tool axis control, which is how we point the tool at all times, what vector the tool is traveling along at any point in that tool path. And then we have collision control, which is how do we handle exceptions or other unique scenarios that may come up during the course of our path. And with each of these control methods, we have a varied list of strategies that we could use to apply to the tool path. So for tool axis control, controlling the actual pointing direction of the tool, we could stay normal to a surface or a plane. We could define specific angle offsets off an axis or a surface, or we could simplify things and go down to just lines, chains, or points, which we're going to talk about in this webinar specifically. So these are the strategies that are going to create the actual toolpath motion, the initial motion on the part. On top of that, we layer collision control strategies. These are basically modifiers in terms of how do we want to deal with unique situations along the initial path. So we could retract the tool to avoid a bolt or a clamp. We could tilt the tool to avoid an overhanging ledge. We could trim the path and relink it if we have a big tool that can't get into a small corner. We could stop the toolpath calculation at some predetermined point along the path. So these are all modifiers layered on top of the initial calculation. So they're not going to determine the core pointing strategy of our multi-axis motion. They are, in essence, reactive, not proactive, in generating the final motion you see on the part. So with those concepts kind of laid down, let's jump into a simple example. And I'm going to turn off my webcam, and we will jump into Mastercam, and we'll look at a very simple part. And so this is a morph path, and I have a 1/4-inch ball end mill that I'm staying fixed to axis, so basically a 3-axis path right now, and I'm kind of swarfing this bottom fillet here. And I purposely turned off collision control right now. So when we come to the end of this, where there's this overhang on this part, we have this collision. So we need to generate some multi-axis motion to deal with this collision. So if we jump into this morph, let me copy this down. In tool axis control, I'm fixed to the z-axis. So if I want to modify that motion to avoid that ledge, maybe I'll turn on a collision control strategy to tilt the tool if it comes in contact with the end overhang there. So simple enough. Let's generate that and see what we get. So now if we look at this motion, we're staying vertical all the way along the path until we get to the end where this overhang is. And then you can see that right about here, I start to kind of feather out that motion, and I'm now tilting the tool to get down in this last area and avoid the overhang. So as we come in here, it also does something that I didn't really initially picture in my head. It starts to, instead of changing the lead lag angle of the tool, it starts to side tilt around this flange. And I get a lot of tilt motion while the tip of the tool isn't really moving very much. And that's kind of not what I want on this. This might cause scrubbing issues or surface finish issues. I had pictured in my head the tool just feathering out along one direction of tilt to get the rest of that corner. Let's add some further complexity to this and turn on level 3 here. We've got a clamp that we might need to avoid as well. And let's add this as a check body in the collision control strategy. So we want to tilt around this clamp too as we travel along the path. So here's the motion result from this. So I'm staying fixed to axis until I get close to this clamp, and then I've again got all this tilt motion that's added automatically to tilt around the clamp. But again, this is a lot of tilt motion and a very short linear travel at the tip of the tool. And it's really not what I want. I pictured kind of a flowing path to swarf this fillet in essence, and this is reactive, right? This is a collision control strategy that's simply reacting whenever an object's in the way. And it's not creating the nice clean motion that I really want for this path. And that's kind of what you get with the collision control strategy. It's a black box that you're allowing the software to automatically try to fix things. And anytime you do that, you run the risk of getting a result that isn't what you envisioned. So how can I drive this a little smarter and build the intelligence of that clean motion into the tool axis control strategy rather than this collision control calculation at the end? Well, for this one, it's going to be a piece of wireframe, as I imagine you could have predicted. And I've just made this spline on level 4 here, tool axis control line, and it's literally just an offset of a wireframe edge of the top of this part. And I want to use this to drive the motion in this path. So I'll jump into this morph, and in tool axis control strategy, I'll change this to from chain. And the strategy here is going to be closest point. And I'll select this chain. And what that's going to do is it's going to say for every point generated along this path, I want you to point the tool at the closest point of this tool axis control chain. So the theoretical center line of the tool must pass through this chain at every point along the tool path. So that's really simple to draw, and it's really simple to enable. So what does that give us for motion? So now we start off with a tilt that will naturally avoid the clamp, and we don't even need to modify the path for collision control. And this is a real gradual angle sweep along the entire part. And as we get to the end of the path here, we start sweeping out and naturally avoid that overhang as well, simply as a result of where we positioned our curve. And if this sweep looks too abrupt, if we're feathering too abruptly, I can simply modify my chain to modify the motion I get. So I could say I'm going to shorten my tool axis control chain. I shortened it about 1/2 inch. Let me regenerate that. And because I always have to be pointed along that chain, what happens when I reach the end of it here is I'm still pointing at the end and I'm feathering out the path along a greater distance. So I don't get such abrupt tilt motion right at the edge of that overhang. So that's just approximation, right? I didn't have to have anything specific in terms of measurements to create that spline. And I'm just approximating, shortening and lengthening it until I get the motion that I picture. So that's a really simple example. So now let's take this concept and let's apply this same methodology to a very complex part. So here we have an impeller, which is traditionally a pretty difficult shape to program. And I would like to make a morph that hits these orange surfaces on the impeller. And we've got some challenges to do that, right? So we've got to essentially thread the needle here in between the vanes on this impeller. And there's a really small gap in between the leading edge of the vanes. Things open up past the vanes up here, but we've got this choke point, and then we've got to follow that choke point down for some distance. So this is going to be something that isn't initially very evident what you would do to control this well. So I set up this morph, and I've purposely turned off collision control to start out with here. And what I'm doing for tool axis control is I'm pointing the tool based on the surface normal vector. So this is kind of the result that we get. So we're staying normal to the orange surface. And you can see because of that, we immediately have issues going through the throat area of the impeller, right? We're massively colliding here. And we've got that collision almost all the way down to the end of the orange surfaces. But the actual tilt motion looks pretty nice. If I can just get it to go through that throat area, it wouldn't be too bad. If I just handed all of this off to collision control and I said tilt automatically however you think is best, it might make a mess of this because I've handed it something that, like especially in this area here, it's not even close to a valid path. So it's going to have to change the tilt radically by almost 45 degrees to get it through this throat area properly. So again, I don't want to hand it off to that black box and possibly get a result I don't expect. I want to get to the motion I picture in my head. So I can do that with wireframe again here. So let's show a really cool trick to this. If I look at like the very last pass on this morph, the motion actually looks close to acceptable. I have a little gouge here, but as I come up the floor, I actually come through that throat area correctly. And really, it wouldn't require much tilt at all to make this a valid path. So that looks pretty good. So how can I take that motion and take the concept of that motion and apply it to the rest of the path? Well, I'm going to do that through another from chain. And so right in backplot here, I'm going to do a couple things. First of all, right at the start of this last pass, I'll position my tool and I'll hit restrict drawing. And that will clear the backplot up to this point off of the screen. Now I'm going to hit the S key and step along that last pass of the part. So that's the pass that I kind of like the motion on, and I want to try and carry that forward. So what I'm going to do here is in the options for backplot, I'm going to turn on tool vectors and give them a length of 1 inch. And when I do that, for every point along the toolpath, I get a vector line. So I can kind of see my tool pointing direction along the length of this pass. So what I want to do is rip this out and try to use it in my path. So I can save backplot as geometry here. And when I do that, what it does is it saves everything currently displayed in backplot as lines, arcs, segments on whatever level you specify. So I'll save this to level 3000. So now if I jump out of this path and I'll turn the impeller off, this is what's on level 3000. This is all wireframe geometry that you can utilize however you want to. So I want to actually create my from chain off of the vectors of this pass because I really liked the motion of that singular pass. So I can come in and I can say wireframe spline manual, and I can just make this really approximate spline along every 4th or 5th tip of these vectors. And I'll come down, and I won't actually go through this vertical transition here. Maybe I'll just come to the end of the initial swoop that got us through the throat area safely. So now I've got this spline that I know gets through that throat area nicely, and I can use that to control the motion of the path. So let me copy this morph down, and let's use that as tool axis control. And here I put it on level 4 and cleaned up the vector so we can just start using that. So this is the spline that I'm going to use to control the path. And this is something that would be impossible to just draw freehand or think of unless you had, that initial good pass and good vectors to pull out. And again, this is all approximate. So I'll change my tool axis control to from chain. And I'll say for start to end for each contour. So I want to move along that chain for each pass that I make, zigzagging along this part. Now I know I'm still going to have some slight collisions. We saw those slight collisions in the last pass. So I'm still going to turn on a collision control strategy. But now when I do that and I tell it to avoid these blades, it only has to change the tilt of the toolpath a couple degrees in order to avoid that collision. And it's not really going to change the vision of how I wanted this tool to react through this impeller. So let's give that a shot. So this is the toolpath we get. And let's check out that transition through the throat area. And let's turn off these vectors so we can see this properly again. So we properly come down through the center of that throat, and we avoid everything. And we clear the holder, and then we sweep out to the end of the floor. So for every single pass on this part, we've taken that good motion that we found in the last pass, and we forced it explicitly for everything in this toolpath. So we've just programmed this really complex throat area using a simple wireframe spline that took us about 3 minutes to generate from scratch, and it's totally approximate.
Dylan, do you mind if I jump in and ask a quick question for you?
Sure.
We have a question in the chat. How do you determine the distance for your driving spline? So how far from your drive surface do you generally create these splines? This was asked actually on your last example, but it's really a good question for both, I think.
Yeah, so that determines, or it's based upon what you want your tilt to look like. So if we go back to the last example for a second, if we raised up this spline And remember that our toolpath is now tied to this geometry. So if we change the geometry, the toolpath will go dirty and we'll regenerate it and the motion will change. So if we just approximately, that was probably a 2-inch rise, it changes the angle the tool has to point through. So in this case, I'm actually still avoiding that clamp, but the tool is remaining much more vertical. So really, I'm not using any specific numbers here. I'm not using whole numbers. I mean, that was literally a by eye move that I made to change that drive spline. And the closer your from chain is to the actual surface you're cutting, the more extreme the angle change is going to be as you transition across the surface. The farther away it is, the farther away you're putting the pivot point essentially, and the less angle change you're going to enact upon the toolpath. So depending on your goals for the toolpath, you'd either move this drive chain closer or farther away. And if I go back to this impeller example, if I was concerned about that in this path here, when I made that backplot geometry that I used for the pass, I used a vector length of 1 inch. But I could very easily make that 3 inches here. That gets a little messier to look at here. I've got a lot of passes on screen, so maybe I'll restrict drawing. And let's just look at that one path. So you could create your spline out here, and you'd maybe have less tilt motion in the actual final path. So the core concepts here are, I baked in my good motion, my pure motion, right into the tool axis control. So I'm explicitly telling MasterCam what I want out of that tool pointing before I ever have to modify or change it up with a collision control strategy. So that results in a super, super clean toolpath, and it's easy to envision what the end result is going to be because you're not feeding all this motion into a black box that's going to make radical changes. This is just making the small final tweaks to this path to get it perfect. And that's kind of the core concept behind using this simple wireframe geometry on shapes like this. So that wraps up my examples. If you have any questions on this, please feel free to enter them in the question pane. And don't forget that you can also follow up with questions on our YouTube channel when this video is posted. So Jesse asks, how can you show us your drive geometry for the first morph example? So that would be this simple morph example I believe Jesse was asking about. And I was wondering if someone was going to ask about this because this is kind of a nice trick in morph to do things like single sweep a fillet. So for this morph example, I'm patterning from the top of the fillet to the bottom of the fillet. And I've got the fillet as my drive geometry. But when I tell it how to cut this, I say, instead of the default full start and end at exact surface edges, I say determine by number of cuts. And I say, I only want one cut on this path. And that will place a toolpath right down the center of that drive surface. So it's really excellent for doing things like this, driving a ball right into a fillet area like this and doing a single swarf pass. And it's also really good for getting the approximate center line motion too, to generate drive splines on more complex shapes. So Adam asks, can you explain the different types of tool control? To chain, from chain, surface, etc. So I won't touch upon much of the extensive list here, because this is really, we could spend many more webinars on this. So surface with tilt, these kind of tool axis control methods, you're taking into account the surface normal direction, the vector of your drive surface at every single point in the path you're crossing. So in cases like that, you're basically modifying your tilt in relation to that surface normal at all times. Things like angle towards tilt axis, fixed angle to axis, rotated around axis, you're more basing your tool pointing strategy on the actual machine rotary axis positions. So you could lock it to a specific angle off Z, X, Y, etc. And you're not so much taking into account the surface normals. And then from point to point here, you could do things like 2-point drive towards the center of a sphere, or from point, picture basically hanging your tool by a string and you're holding the string up in the air and you're swinging the tool around, and all of your motion has to pass through that single point. So this is a good strategy for doing things like undercuts in bores and things like that, where you're always pointing back towards some center line out in the distance, but tilting the tool off to allow clearance. And same thing with from chain and to chain, except you're allowing that hinge point essentially to move along a spline or a chain out in space. And then you have different ways to manage how you stay relative to that chain. So in these examples, we used two of these strategies. We used closest point and we used from start to end for each contour. And those are probably the most common strategies to use in cases like this. So David asks, on your first example, can you use an offset drive surface? And does the drive surface have to be below the cutting surface? So I think you're asking about clean core methods, where you're pathing on an initial simplified surface and then offsetting to the final surface. And you can certainly do that with this style of tool axis control. So this is, very simple to set up, but it's very powerful in that you're getting the exact angle control you want on the tool. And it's not limited to these specific examples. I tried to show a very simple example and a very complex example to show how I use this day to day for both. Thank you very much for attending, and I hope to see you in the next one. Take care.